Katrina is going to be coming, and Katrina works at Slack, and they put out, along with her co-author, they put out one of my favorite pieces on recommender systems this year. And so it is an absolute pleasure that I get to introduce her, because I know that when the blog post that she put out came out, there was a boom in the MLOps community Slack with this blog post. It was incredible. Katrina, you around? Where are you?
Here, if you can hear me.
Yeah.
Hello.
All right. Success. So you
Thank
didn't
you.
realize there was going to be some ASMR haircut while you were getting introduced, did you?
Yeah, I'm quite surprised.
Nice. Well, I'm going to hand it over to you. I know you got an awesome talk, and we'll be back. Next up, I'm going to be playing some music. So everyone get your prompts ready on what kind of songs we should make about data and data pipelines. In the meantime, Katrina, it's all you. The floor is yours.
Thank you. Hi, so hello everyone. I'm Katrina. I'm a machine learning engineer from the ML services team in Slack. So I'm ready to be here and talk about the recommend API, which is a unified end machine learning infrastructure to generate recommendations across Slack product functionalities. Our team has spent the year to build. So just here. So first, a little bit of the introduction. I believe most of you probably know about Slack, but you may just know it as an instant messaging program, which is unfortunately also what you hear. And it's also kind of my impression before Slack. But after I've spent some time working in Slack and see how Slack has utilized its own platform to organize information and collaborate work, and to reduce the email usage, at least internally, to zero, that I realized Slack from just a messaging app can in fact become our digital HQ. So there are so many features in Slack to help you become more productive in work. Channels and threads have always been here, but I wasn't aware of this until I joined Slack, that we can organize channels into different sections to help prioritize information and reduce Slack fatigue. We can integrate various industry-leading software and custom apps right into Slack. So that for one thing, we can bring all our work communication into Slack. Slack Connect is recent, which enables us to connect with external stakeholders as if they were internal. And Huddle is also very new and stands out as quite a unique tool to communicate with a team, which is also very, very well received among Slack users. I don't think I'm allowed to share more details yet, but I can tell you that there are still quite a lot of new features lined up to be released. And I'm just really excited to see this much innovation happening in Slack all the time. So Slack is a great platform, and it presents many opportunities for recommendations. Although the way our team operates might be a little bit different from other P2P companies, where the business model is mostly reliant upon a highly performant recommendation system. So for those, there are usually one or two prominent use cases, and often multiple teams operating under the hood. Instead, our team's mission is to help Slack build better product and work more efficiently with machine learning. In another word, we aim to simplify the user experience and make it more delightful, which means we want to integrate recommendations into not just one or two, but as many use cases as possible. So what are those use cases, and where is ML currently used in Slack? For example, Composer DM is where we suggest additional candidates to add to the conversation. Creator invite flow is where we suggest top contacts to invite to the workspace based on team creators' Google Calendar events. We have two variants of the Slack bot channel suggestion. Where we suggest channels to leave or archive based on users' activities. The channel browser recommendation, the default sorting, where when users want to view channels, and invite send time optimization is where instead of always a reminder at the static default time, personalize the send time based on inviters' activities. Since the blog post Demetrius just mentioned earlier, which is this talk is mostly based on, the team has have successfully implemented and launched 2 new features. One is the huddle invitee recommendation. The other is to suggest similar channels when users are joining a new channel. So as you can see, the team have managed to integrate recommendations into various product functionalities, all thanks to the Recommend API. I also mentioned an important result of the Recommend API, aside from the current use cases that can be found in the product. There are near equal number of use cases we are currently prototyping, have tried and abandoned. So the Recommend API really provided us with a unified infrastructure, makes it extremely straightforward to bootstrap new recommenders and empowered product teams to test and discover whenever machine learning makes sense. And before I dive into introducing this unified infrastructure, I'd also like to talk a little bit about dependencies. Some of you are probably aware that there are a lot of tools for MLOps in the market at the moment. For each phase, I kind of always felt there are sometimes more tools that we can choose from. So, however, fortunately for our team, we don't usually have to go through a lot of that trouble. One thing is because Slack has a really well-maintained data warehouse ecosystem, which indeed saves us a lot of the headaches. For example, we use Airflow to schedule various tasks. There are tools to log user activities. Therefore, we can ingest and process data from various data sources, including those logs, into the data warehouse, where we can query data interactively and creating dashboards from it for visualization. There's also something similar in Slack that we built internally to feature store. It enables us to look up computed data from that service with primary keys in real time. Although we internally we don't really call it feature store. I think it's because at that time store is not a concept yet. But this is something we can do. There's also an experimentation platform that we can run A/B testing so that we can decide which feature we want to launch or not. So even before we have this Recommend API, the team has spent quite some time building embedding service and the signal service. So the embedding service is used to, if you are familiar with the term embedding, is used to fetch and store common Slack entities based on semantic or word graph vector encodings. The signal service is built upon the feature store I mentioned earlier, where we can fetch features the team have collated for various Slack entities in real time. Both embedding service and signal service are also used extensively. And after we have built the foundation of Recommend API, the team also spent some time working on having the model training service and model serving service. Model training service provides us with an Airflow operator to train and deploy ML models, and model serving services enables us to make predictions and rankings in real time. So how does this unified recommendation workflow work? Obviously, it isn't realistic for us to create a customized for each use cases we want to integrate recommendations with. So we need to make it really easy to bootstrap new recommenders by sharing common infrastructure. One thing we did to achieve that is avoiding chasing the metrics. So we don't really use overly complicated engineering and models. This is made since our service has provided us with a common solve for various entities. Plus, we usually go for models such as Logistic and XGBoost with just a little bit of hyperparameter tuning. So the offline training pipeline will mostly end up with at most 4 steps, log transformation, imputer, and an estimator. Another thing is that we have to be really careful about how we organize and think about the various components. At a high level, recommenders are categorized according to corpus and then source. Corpus is a type of Slack entity, such as a channel, Slack channel, or user, and the source corresponds to a certain use case, where each source usually maps to a single recommender. For example, I've listed two of the use cases discussed earlier, the channel browser and Slackbot channel suggestion. Both of them belong to the same corpus, which is the channel, but different sources, therefore also different recommenders in the code base. Regardless of corpus and source though, the treatment of each recommendation request is pretty similar, which works like this. So here you can see the four microservices I mentioned earlier in red here as the backbone of the recommend API. And we have the end that serves the request, takes in query, and returns a set of recommendations based on the corpus and the source. At the same time, we will log the recommendations. When user interact with those recommendations in the front end, we also log those user activities. Offline in our data warehouse, we use Airflow to run tasks, combine those logs into train new models. We also emit various metrics from different components overall process. Diving into each component in a bit more detail. In the back end, each source is associated with a recommender, and we sequence of steps to generate a list of recommendations. We fetch relevant candidates from various sources, including our embedding service. Then we filter candidates based on relevancy, ownership, or visibility. We augment features with our signal service, and then score and sort the candidates with predictive values generated by the models. Sometimes we also re-rank candidates based on additional rules. So each of these steps is constructed as a standardized class, reusable between recommenders. Each of those recommenders is in turn constructed as a sequence of steps. Here is the entry point to the recommend API, where we will pick corresponding recommenders based on the source and corpus. And the aforementioned two use cases, channel browser and the Slackbot leaf suggestion, will look like this. Each of them is constructed of a fetcher, a filter, which models we are using, what features we are logging, and sometimes a re-ranker. By comparing these two recommenders, we will see, first of all, components can be reusable. For example, these two recommenders can be sharing a filter while using a different fetcher. Features are most of the time also a shared components. In this case, these two recommenders belong to the same corpus, which is channel. So we usually just log all channel features we collated in signal service, and we will further process it in model training. Also, we can just here, channel browser has a re-ranker while Slackbot suggestion might not. So we can see a lot of times creating a new recommender is really a matter of having a new fetcher or filter. Then we can utilize and plug in different combinations of existing components. I've briefly mentioned that besides being able to serve recommendations, the recommender also handles logging, such as tracking the initial request that was made to the API, the results from it, and the features our machine learning models used at scoring time. We then output the results through an API to the end, where we will log user interactions. With that, we schedule flow tasks to join logs from backend, which provides the features, and front end, which provides the labels for training machine learning models. Again, we will differentiate data for various use cases by using additional fields for and then source. Models are then scheduled to be trained in Airflow with the model trainings, which springs up cluster with loaded Docker image to train the model. With that, we score the candidates with model serving service and complete the cycle. Thereafter, we can start a new cycle of logging, training, and serving again. For each source, we often experiment with different sets of features and various models. For example, you can see here for people browser, there was a time when we were training and experimenting with 6 models. We set things up to make sure it is straightforward and productionize new models. Here is the examples where we are adding new models to for aforementioned use cases, channel browser and stackbot leaf suggestion. We are training a anchor for the channel browser and a classical XGBoost for leaf suggestion. Again, we specified source and corpus so that we would ingest and process data for corresponding use cases. We also indicate with feature specification here, which features we want to train our models on. Most of the time, this is really all the code we need to train new models. Although I'd also like to emphasize that it only seems to be this simple because we've been iterating and putting a lot of thoughts into the code structure, overall design, and extensibility. We output metrics in various components so that we can get an overall picture on how the modeling. It's also based on the shared infrastructure. So usually when a new model is productionized, metrics will be automatically updated to track its performance. For example, reliability metrics is the Prometheus metrics emitted from the backend to track the number of requests and errors, which is super helpful to monitor when we make changes to the backend. Efficiency metrics is also Prometheus metrics from the Kubernetes cluster in the model serving service so that we can track if the cluster is healthy or not. Offline metrics is what we get from offline training jobs so that we have metrics on both training and validation data set to compare various models and decide which one we potentially want to expand and productionize. Feature stats is used to monitor feature and feature importance. Do a bit more detail with the online metrics. It's really business metrics, which we share with the external stakeholders. Some of the most important metrics we track acceptance rate, which you may know as click-through rate sometimes, and ranking metrics, such as discounted cumulative gain. Online metrics are frequently checked and monitored to make sure the model plus the overall end-to-end process is working properly in production. Here is an example of the offline metrics for both the training and the validation data set. We can see from the graph to what degree the models are overfitting, and we can also track the metrics over time. Here is an example of the reliability metric backend, where we are tracking the total number of requests and the error rate. So in order to train them, we need data, both features and labels. Most often we'll target active Slack users, so we usually have features to work with. However, without a model, we won't be able to generate recommendations for users to interact in order to get the responses and generate labels in the first place. This is one variant of the cold start problem, which is called new community. For us, it's really lack of user interactions to train the model to begin with. The other two variants of the cold start problem are new user and new item, which some of you are probably more familiar with. Our team have managed to mitigate this problem by utilizing what we call a hand-tuned model. So during the first iteration, we'll generally rely on a hand-tuned model, which is based on common knowledge and simple heuristics. For send time optimization, for example, we are mostly likely to send invite reminders when the team or inviter is more active. At the same time, we brainstorm relevant features and begin extracting from the signal service and logging all of them. Now that users have something reasonable to interact with, this will give us the first batch of training data so that we have the trained model to iterate upon. But how do we know that any of the changes is working? We rely extensively on A/B testing to make sure ML models are doing their job to improve the recommendation quality, before we launch anything. Whenever we switch from a hand-tuned to model-based recommendation, or experiment with different sets of features, or more complicated model, we run experiments and make sure the change is boosting the key business metrics. We will often be looking at metrics such as the acceptance rate, successful teams, or other metrics related to specific parts of Slack. We've since managed to run quite some successful experiments, so the process obviously works. And I'm going to go through a list of recent wins we've made, the aforementioned ML-powered features. They are all measured in acceptance rate. For example, there are a 40% increase for Composer DM when transitioning from hand-tuned to logistic regression, and an additional 6% from logistic regression to XGBoost. For creator invite flow, we saw a 15% increase from hand-tuned to logistic regression, and over 100% improvement from hand-tuned to XGBoost for leave suggestion, as well as a 32% increase for Slackbot archives. There's also a 15% increase for channel browser recommendation. Additionally, Huddle invitee recommendation is a very recent experiment we've successfully run, and we saw a 10% improvement from hand-tuned to XGBoost. Here shows the impact measured in acceptance rate of two of the experiments, the Composer DM and the channel browser over the time. In summary, we developed a unified framework we call the Recommend API, with us to quickly bootstrap new recommendations behind an API that is easily accessible to engineers. Behind the scenes, those recommenders reuse a common set of instruments for every part of the recommendation engine, such as data processing, model training, candidate generation, and monitoring. This has allowed us to deliver a number of different recommendation models across the product, driving improved customer experience in a variety of contexts. Last but not least, I'm presenting here, but it's really a teamwork. Here I've listed the current team members, but there are actually more people than I list here who have been making contributions over the year to make this work. I just really wanted to take the time to thank the team and thank everyone for being present for the talk. Yeah, I think so. We still have some time left, so I'm gonna be available to answer some questions.
Amazing. Thank you so much. That is awesome. So we've got a few great questions that are coming through, and I want to choose the best of them. Sam, good old Sam, shout out to Sam. What's happening, man? He's asking if you can elaborate on what you mean by hand-tuned models.
So the hand-tuned model is really something like, so we have this signal service, we have this feature store and signal service. So hand-tuned is really like we kind of brainstorm what kind of features will boosting the performance of this particular use case, and then we just get those features, and we have just like a manual weights. It's not really trained by any models or something. Like we think based on just common sense, this feature will boost the performance, so we give it a positive weight. So it's really like a combination of these features and weights as the first iteration of the hand-tuned model. Yeah. If that makes sense.
Awesome. Yeah, super cool. So Ziheng is asking about, it seems like the training data only depends on the features that have already been extracted in this loop. I imagine there's also some way to come up with or experiment with new features. How is that done?
Yeah, so we can still be adding like new features to the signal service, or sometimes we will calculate some additional features in real time. When we are working for this use case is the invitable, or yeah, and which is based on which the features is based on Google Calendar events, and it's not present in the Signal service. That's where we will just calculate a bunch of features based on like the JSON output from the Google Calendar API in real time, and then we can just log those data, and then we can do the normal training, like the cycle as well. The feature doesn't have to be from the feature store, but like the feature store is just really convenient kind of a pool of features that we sometimes we will go to, just like I'll kind of just go to first.
Makes sense. I see. So George is asking a killer question. Model training kicked off via Airflow. How often does it get retrained?
Yeah, we actually have like a scheduled Airflow task to retrain it every day. Like so, but we don't deploy it every day, I would say. Like, but like, yeah, we have this talk with Shaurya about like the ML ops interview study, and then yeah, it is as a matter of fact, like exactly what the interview study said. We just retrain the model every day to prevent feature just feature shift, and yeah, and yeah, that's pretty much, yeah, we just retrain it every day.
Excellent. Well, thank you so much, Katrina. This was awesome. And I want to give everyone a little sneak peek that Katrina is going to come on to the MLOps Community Podcast, and we're going to talk even more about this. So that should drop hopefully in like a month. I think we're going to be recording it. So yeah, stay tuned for that. That is the MLOps Community Podcast. And thanks again. This is so cool. I appreciate you going into it. If anybody has not read the blog post, we're leaving a link to that in the chat.